Good afternoon, everyone. My name is Andrea Clark Spence, and I'll be your moderator for this evening. Welcome to another session in our science seminar series. So far, we've had some great presentation, and of course, I'm sure the others will deliver as well. For next week, we have a presentation entitled Using iNaturalists to Document Species Adventures in Southwest US. And that will be presented by Dr. Pamela Rutherford. For this evening, our presentation is entitled Impact of Evolutionary Earth Changes on Global Temperature and Carbon Dioxide. The Earth has been changing and evolving for 4.5 billion years in relentless cycles within cycles within cycles. In this talk, we will examine some of the evolutionary changes and interrelationships over deep time between carbon dioxide, water, climate, life, and tectonic events. How did they impact each other, and who is controlling who? Where did carbon dioxide come from, and where did it all go? Is the Earth heating or cooling? What are the tectonic and other driving forces behind these relentless changes? Ultimately, do paleoclimatic trends tell us about the current climate, and can the past history of the Earth give us insight into the present and future? Where is planet Earth headed? Join us for this fun and challenging romp from the ancient Archean geological past to more recent historical times as seen through the lens of geoscience. Our presenter today is Dr. Hamid Mumin. Dr. Hamid is a professor in the Department of Geology, Brandon University. He was born in Toronto, grew up on a farm near Milton, Ontario. He graduated from geoengineering at the University of Toronto in 1985, completed his Master's of Applied Science in Economic Geology at Toronto, and subsequently a doctoral degree and postdoctoral fellowship at Western University. He's a professional engineer and geoscientist and conducts research in a variety of disciplines, including resource development and green technology. He is a past president of Geosciences Canada, the National Board of all Provincial and Territorial Engineering and Geoscience Association that advises on professional standards, education, and regulation of the profession. He's a former member of the Brandon University Board of Governors and current member of the Brandon University Foundation. Ladies and gentlemen, I present to you Dr. Hamid Mumin.
Thank you very much, Andrea, and thank you all for coming. Welcome. Hope you enjoy the talk. I hope it'll be a little bit controversial. So I'll give you a simple outline, okay? Introduction, we'll give you some background information, talk about CO2. So I want to give you some background information because some of the basic facts related to this subject impacts how we interpret what happened in the past. And we're also going to ask the question, can the past help us interpret what's going on in the present and even into the future? So we'll talk a bit about paleo warming and cooling, climate drivers, past and present, and then some summary and reflections on what we're talking about. Okay, so why do we need why should we have a geoscientist perspective on the subject? Well, the interesting thing is that geoscientists have been documenting, not just studying, but documenting changes in the Earth's climate, environment, and life for more than 250 years. Nobody sounded the alarm, 100 years ago, and why haven't some of us, anyways, sounded the alarm today? So we can ask the question, to what extent does Earth history play a role in our understanding of this modern climate concerns? And is the science of the set, as some people would have us believe? And I'll just say one thing, and that is, if it's settled, it's not science. Okay, so we'll carry on. So I'd like to start at the beginning. So you all know what the atmosphere is composed of: nitrogen 775,000 ppm, oxygen 208,000, argon 9,300. Water vapor varies 10 ppm if you're in the South Pole, and maybe 40,000 ppm if you're in a tropical rainforest environment. And we have a little bit of CO2 here, coming in at about 425 ppm currently, and a few other trace gases in the mix. So what we're interested in is greenhouse gases, right? So what are they? And as it turns out, water vapor, okay, is the dominant greenhouse effect. It counts for about 95% of the entire greenhouse effect on this planet. And of that, about 0.001% is a human contribution. Carbon dioxide comes in next at about 3.62%. This is of the total greenhouse effect. And of that, 0.117% is the human contribution. And this is what we're told is the tipping point, okay, or tipping the balance, let's say, not tipping point, but tipping the balance. And then there's a contribution to the greenhouse effect from methane, nitrous oxides, and a few other miscellaneous gases, which are relatively minor. But at the end of the day, when you add it up, 99.72% of the greenhouse effect is natural, about 0.28% human contribution, 0.117% of that is the human CO2. Okay, so what is carbon dioxide? Okay, I like to call it the miracle gas for good reason. It's colorless, tasteless, odorless, polar molecule. And you can see from the diagram that, let's see if we can find our pointer. Yeah, it has both two negative charges, positive center, and which makes it a dipole, acts like a dipole or a little magnet. It's a sticky molecule, and it likes to stick to other charged things. In particular, it likes to stick to water, because water is also a polar molecule. This is what gives water its capacity to absorb and hold CO2 in solution. So aside from all these other things, CO2 is foundational to all life. I'm sure we all understand that. And it is in fact the original quintessential plant nutrient. So here's a satellite image from NASA. Basically what it's showing you is the change in global greenery, global greening in the 33-year period leading up to 2015. So the dark green is greater than 50% increase in what they can measure as leaf coverage. The red areas would be a decrease in plant coverage of about 15 to 20%. So on the whole, the planet is greening dramatically, okay, which is resulting in things like huge increases in crop production and many good things. And amongst that, the increase in greenery also has a moderating effect on surface climate. Sahara Desert in the 35 years or 33 years up to 2018 actually shrunk by about 8%. Most of this we can attribute to CO2, some to the slight warming effect that's going on. Okay, so I want to talk a little bit about CO2, where it's coming from, balance, and its residence. Okay, so inputs into the atmosphere. First of all, there's the human input, okay, which we'll call significant, even though it's nature, volcanism, animals, plants, soils, decay, vegetation, and so on. That's a major input, and ocean degassing. So basically, cold, warm oceans release CO2 to the atmosphere. That's another major input. So removal of CO2 from the atmosphere, cold water, oceans, absorbs CO2. It's a major sink. The biosphere capture, both terrestrial and marine, and its conversion to organic material and rocks, coal, peat, etc., etc. That's a very significant sink for CO2. There's chemical capture and destruction, so a little bit gets converted into carbonic acid and things like and rock as well. And precipitation removes a certain amount of CO2. We'll call that significant or minor. So I have a question for you right now. And does anybody know what the residence time of CO2 is in the atmosphere? That means the average time that CO2 hangs around in the atmosphere before it gets recycled by any of these other means. The most recent paper I read was 4 years. Okay, back 30 years ago when I first started teaching, the textbook said 6 years, but the more recent is 4 years. Okay. So do the math. You know how long it takes the nature to recycle the entire annual human output of carbon dioxide, which is about 35 billion tons these days. Do the math. It's 15.4 days, assuming that 4-year recycle time limit. So the point is that the cycling of CO2 through nature is very rapid. So that's the only point of pointing this out. It doesn't hang around. Like we've been told that the molecule of CO2 can hang around for 1,000 years or whatever. I say that's wrong. It can hang around for, in fact, for 1,000,000 years if that particular molecule never gets captured by either of these other means. But the average residence time, 4 years. Okay, so some of the behaviors that are impact what we're going to talk about. CO2 is absorbed by water in the atmosphere, oceans, and some reacts to form by carbon and carbonic acid. CO2 is a heavy gas, so it would hang around your surface, except that it gets captured by H2O, and that is what carries it throughout the atmosphere and distributes it fairly efficiently. CO2 does absorb heat, and when it absorbs heat, it's a kind of a linear molecule, vibrates like a tuning fork, and then it rapidly re-emits the heat that it absorbs. It actually has a very low heat storage capacity. Water, on the other hand, has a tremendous heat, energy, storage, absorption, okay, and distribution capacity as water, vapor, ice, okay, and liquid, both on land, sea, and in the atmosphere. So the redistribution of energy by water, in fact, is so efficient that it results in rapid weather changes, and we all experience that almost every day of our lives. Okay, now getting into the origins of CO2. Where does it originate? Where did it come from? It originates with volcanic activity, okay, along with water. And how is that? So I'll take a couple slides to get through it all. But you know, here's well, this is Mount Pinatubo and Phillips around in 1992. Right now, okay, there's about 1,511 what are classified as active volcanoes on land. Of those, 46 are in continuing eruptive status as of 6 August 2025, and that's according to the Smithsonian Institute Volcano Observatory. Okay, so just for a moment, imagine how much water and CO2 vapor does it take to volatilize 10 cubic kilometers of magma and blast it 40,000 feet in the atmosphere as an aerosol. Okay, it's a fair bit, but this is a felsic material. It is actually high, has a very high water content, but it has a low CO2 content. So not a lot of CO2 from this type of volcano, but most land volcanoes are of this type, felsic to intermediate. I brought some samples, but we don't have time to look at them. So granite would be an example of a felsic, low CO2 magma. This is Kilauea, Mauna Loa, the largest active volcano on the planet right now, in its basaltic volcanoes, which is a very high CO2 content and a relatively low water content. Then we can get up to about 15% carbon dioxide dissolved in these basaltic magmas. The most important global CO2 observatory is right here on the north flank of Mauna Loa. So there are several others around the world, but the one that most often is over here. Now this is just for your entertainment, but this is Ogonyo Langai, Mountain of God. It's in the southern end of the East African Rift in the country of Tanzania, and it's essentially a baking soda volcano. It's actually we call it a nitrocarbonatite. It's sodium, potassium, carbonate magma is erupting. And it erupts at such low temperature that you actually can't even see that there's an active eruption taking place unless you're at night, and then you can see the red glow of this nitrocarbonatite magma that's coming out. And the rocky material from that has a CO2 content about 40 to 48%, so it's very high. But along with the magma comes huge amounts of CO2 gases. Now these are very rare, okay, but it happens. The third type of CO2 rich eruption that I'll mention is kimberlite magmas. They originate in the relatively in the upper mantle, but at depths of about 300 to 600 kilometers, whereas the basaltic magmas and this type of magma, they originate still from the mantle, but at higher levels of the mantle. And they're the CO2 rich ones. Okay, so the interesting thing though is that the vast majority of volcanism is not on land. These are submarine eruptions. It's huge. amounts. And, for example, there's 65,000 kilometers of active spreading ocean ridge where you have upwelling basaltic magmas on an ongoing basis. And another up to 3.4 million off-axis submarine volcanoes, and about 100 to 140,000 of those are actually active. And almost all of these are basaltic high CO2 emitters. And that CO2 emission goes right into the ocean, and you'll see what happens in the ocean. It gets absorbed. So there's a couple of submarine eruptions near Iwo Jima, and here Homitonga in 2022 is actually a very large eruption. They put about 150 million tons of water vapor into the upper atmosphere. So when they're not busy erupting on the ocean floor, there are innumerable hot springs taking place. Some very hot ones, which we refer to as black smokers. A 8 centimeter diameter vent at 300 to 400 degrees and 3 to 4 meters per second output has the thermal output of about a 500 megawatt nuclear reactor. And they're untold, probably tens of thousands of these things we don't know. There's also an estimating about up to 10 million of these lower temperature CO2 rich hot springs, which are continually pumping CO2 into the cold ocean. And there it gets absorbed. One of the points here is that the ocean is heated from above, primarily by solar energy, but it's also heated from below. And it's not just magmatic activity, but it's the general overall geothermal gradient of the Earth emitting heat. It's coming from all the way from the core. Okay, so here's a question here. What's the temperature of the deep ocean and why? So if you're in the Arctic, it's freezing cold all the way down, but if you're in the tropics, the surface temperatures can be 30 degrees, but you go through a steep thermal climb and then you get into deep ocean waters where you've got 4, 5, 6 kilometers of frigidly cold waters, 4 degrees centigrade and lower. Does anybody know why? Why is the ocean so blooming cold? It's because the water is its densest at 4 degrees centigrade. So the melting of the polar ice caps, right, sends cold water, which just sinks to the bottom of the ocean, and you have this ocean bottom current, which distributes that cold water throughout. But the vast majority of the ocean is very cold, which gives us its great capacity to absorb and hold CO2 gas, just like a pop can or a beer can or your champagne or whatever it is you like. Okay? Currently, the ocean holds about 60 times the entire CO2 content of the whole atmosphere, with capacity estimated to be as much as 600 times, which if you do the math, at 35 billion tons per year, oceans can hold about 60,000 years of human CO2 output. Okay, that's just an anecdote. Okay, history of CO2, where did it all come from? Where does this carbon come from? Well, it comes from original condensation of the hot solar disk, okay, that hot plasma, which extended for several hundred million kilometers from the initial solar disk. When its hot plasma cooled, it formed liquid chondrules. Those chondrules further cooled and amalgamated and condensed, and they form these rocky bits. These rocky bits are still raining down on the Earth today, and we know them as carbonaceous chondrite meteorites. And the good old physics department, they actually have one of those if you want to see, or if you ever wanted to hold a little bit of the Earth's outer atmosphere, where it's about 6 to 10,000 degrees centigrade. Well, here it is. Right? It still has the composition is near identical to the outer solar atmosphere from these carbonaceous chondrites. But these are the rocky bits that condense and accreted to form the original rocky material of the Earth. When it reaches a big enough mass, the internal heat is such that the Earth goes through its partial melting process and sweats out the iron nickel core. You end up with the iron nickel core and this huge mantle, primitive mantle, which is very high in carbon. So these material runs typically around 1 to 5% carbon. That material then gets released right from the get-go when you have a hot planet through volcanic and magmatic activity and the direct bombardment, which adds to the volcanic magmatic activity, converts that carbon into CO2. And early on, we end up with a very CO2 rich atmosphere. So this chart here shows current atmospheric composition going back 4.6 billion years. Initially, we had a hydrogen helium rich atmosphere with ammonia and methane. We lost the hydrogen and helium to space. Ammonium, methane, I'm not sure if we lost it or just reacted and break down. But that hot Earth, okay, and volcanic activity releases a lot of water vapor and carbon dioxide. And by 3.3 or so billion years ago, we had an atmosphere of 250,000 approximately parts per million of CO2 along with nitrogen. So we had a tremendous amount of CO2 in the atmosphere, but that slowly disappeared, gets captured and recycled, particularly in the oceans and as carbon minerals and carbon bearing rocks. Okay, and eventually we got to the point of biogenic oxygenation, capture of CO2 and its conversion to oxygen. And we ultimately end up with oxygen, nitrogen rich atmosphere with a bit of argon and a minor amount of remaining CO2. Okay, so we want to get into temperature and CO2, and I just want to say a couple words about measurements. Okay, where and how do we determine temperature and CO2 in ancient geological times? Okay, so paleotemperature, which is typically generally measuring the past ocean surface temperature, it's measured using proxies like foraminifera, and we use the carbonate shells and look at the oxygen and the oxygen isotopic ratio in the oxygen, which is a function of temperature of formation. So oxygen isotopes are actually very good for that. In this case, warmer water favors incorporation of a higher amount of the lighter oxygen, O16. Paleontologists and geoscientists, on top of that, they are always recreating paleo environments from fossil rock and geochemical evidence. And in more recent times, the preferred material to analyze are the Antarctic and Greenland ice cores, where again, you look at carbon and oxygen isotopes, but also the trapped gases, where we can get an indication of CO2 contents, right? CO2 is also measured using other proxies like stomata, boron isotopes, phytoplankton, carbon isotopes, and chemistries of paleosols and like seven. So there's a number of ways, but the important point here is that there are a number of lines of corroborating evidence which gives us our paleoclimatic information. So here's the final result, the last 550 million years, and the red line, of course, is the temperature chart, okay, going back 500 million years. So we're here, zero, this is today, and that's 550 million years ago. And you can see that the temperature, this is global average temperature, oscillates between what is referred to as hothouse conditions, where for whatever reason, the temperature seems to be buffered and stabilized at around 25 degrees centigrade, and all the way down to what are called icehouse and even severe icehouse conditions. So we're getting icehouse means that period of geological time when we have polar ice caps, alpine glaciers, and all those wonderful things like advancing and retreating glaciations, like it just came out of 10,000 years ago. So a 15 to 20 million year icehouse period in the late Ordovician, 40 million year icehouse conditions in the Permo-Carboniferous, okay, back to hothouse in the Jurassic long Jurassic Cretaceous cool period, another hothouse, and then we're into the modern icehouse conditions where temperatures are very cool compared to, in fact, they're the coolest ever compared to the entire history of planet Earth. And we're reaching some pretty severe conditions that you'll see in a minute. Okay, we're here at 2023 at about 14.5 degrees as an average global temperature. And one thing you might wonder is about how does hothouse affect life? Well, dinosaurs sure liked it when it was hot, and so did a whole lot of other things. Plants exploded in the mid-Devonian, both in abundance and in diversity, and the hothouse conditions doesn't harm life as a whole on the planet. Okay, the black line here, dashed line, is carbon dioxide. So what's carbon dioxide doing during the same period? And we can see that, remember, we started with 250,000 ppm, and now by 540 million years, there's a local temporary spike taking it up to about 7,000, but there's this continuous drawdown of CO2. And then we reached a kind of a low period of about stabilizing at about 700 ppm from it's like almost 100 million years, and then it jumped up to a few thousand ppm, about 2,700 ppm, and then it gradually declined. But the main thing that you take from this perhaps is two things. One, nature's constantly acting to remove CO2 from the atmosphere. And there are things that are happening that are putting CO2 back into the atmosphere. Some dramatic spikes along the way. So just to take a look at what some of those things are. What's putting CO2 back in the environment is basically periods of extensive volcanism, okay, huge volcanic outpourings in relatively short periods of time. Let's give you a couple examples only. This is Pangea, okay, started to amalgamate about 330 million years ago when all continents came together as one gigantic supercontinent. And what a continent does when it kind of floats on top of the mantle, and it actually acts like an insulating blanket. So the mantle underneath all continents, it actually heats up. When it heats up, it expands, and you create a mantle plume that rises up. And when that mantle plume, okay, there was one example here about 250 million years ago, rising up, okay, trying to rip apart the Pangean supercontinent, and it results in rifting and massive outpouring of flood basalts. In fact, the greatest outpouring of basaltic magmatism ever, and that's the Siberian preserved Siberian basalts. But that event failed to rip apart Pangea, so it's still there with the mantle heating up underneath. And we had another episode of a huge mantle upwelling of mantle material, which managed in this case to finally rip apart Pangea and open and separate Africa from South America. And we have the opening of the South Atlantic Ocean and huge outpourings of basaltic magmas. Remember, the basaltic magmas are the high CO2 magmas. 30 million years later, another mantle upwelling, and we separated and opened up the North Atlantic, separated North America from Europe. And since that point, 140 million years ago, it's been a steady decline in CO2 content. So I think the next slide is going to take us to this period here, about the width of the red line, which is about 400,000 years. And here it is, the last 400,000 years. So we're here today. In fact, this line here is the current temperature, and the red oscillating line is the temperature anomaly from current, deviation from current temperature. So we're sitting here, and what you see here is a whole series of massive ice ages punctuated by interglacial, the 5 interglacial warm periods here on a 100,000 year cycle. And within that, there are additional cycles. Okay, there's 20,000 year and 40,000 year cycles going on at the same time. So there's all these major oscillations in the Earth's global average temperature. One thing to note is that the current interglacial warm period is cooler than the previous interglacial warmings, and we're 10,000 years in, where the average sort of typical time for these short interglacial warm periods is about 10,000 to 15,000 years. We're 10,000 years in, and some would say that we may well be on the waning stages of the current interglacial. We don't know that for sure. Okay? But this is actually the near the end of the 52nd interglacial warm period in the last 3 million years. So this is just cycling and cycling and cycling. Okay, so what happens to CO2 during this 400,000 year period? Well, when it's warm, CO2 is high. When it's cool, CO2 goes down. When it's warm, CO2 goes up, CO2 goes down. This thicker line is the pre-industrial CO2 level of 280 parts per million. So just to give you an idea of where we're going here with the CO2 oscillations. Okay, but what is not particularly clear on this, because the resolution's not high enough to see it, but warming happens, and several centuries to a millennium and a half later, CO2 rises in all cases. The CO2 rise is following the increase in temperature. You might ask, well, and the CO2 decrease follows the decrease in temperature. So why? Anybody hazard a guess? What's going on? The ocean's warm, it releases CO2, the ocean's cool, it absorbs CO2. So it's a simple cycle going on. And you can see that the oceans have massive capacity to absorb and hold CO2, and they can also release huge amounts of CO2 when the time is desired. Now, just coming out of the last glaciation, okay, when we started to warm up about 14,000 years ago and came out of it rapidly about 10,000 years ago. But when we reached the peak, okay, at the depths of the last glaciation, CO2 was down 182 ppm, very dangerously low for life. So plant species are becoming extinct at those levels. And if we had dropped another 30 ppm down to this level, it's death of all life. Plants can't survive as we know them. They won't survive at that level. And of course, all the animals go with it. So this is, we are the lowest point in CO2 ever in the history of 4.5 billion year history of this planet. And we're oscillating, with a bit of, we're going through these dangerous oscillations from a perspective of life. So here it is, the climate oscillation within the current ice house period. Okay, so this is a NASA image, imaging plants, vegetation cover. I think it's taken probably in the peak summer months. And that's what you see. This is current interglacial, okay? This is a rendering of the maximum of the last glaciation 21,500 years ago. So what we have is boreal forests are wiped out, the tropical forests are gone, replaced by grasslands and copses of trees, and massive desertification. Okay? It's just too cold, too dry, and you've got the CO2 starvation that we just noticed taking place. This is devastating for life in these cool periods. And it's a global devastation, not just in the north where you're covered with ice. Okay, so now let's focus in on the last 10,000 years. So the current interglacial. So 10,000 years ago, we rapidly came out of the ice age. And we peaked, okay, in this current interglacial. We peaked in terms of temperature about 8,000 years ago. And again, I should mention that this is where we are today. Okay, this is today's temperature, and this is just oscillation. Okay, perturbation from the current temperatures, and what they're measuring there is they're taking it from ice temperature as a proxy for that. So we peaked 8,000 years ago. We had a sort of a moderating period, and then we had a second peak about 3,500 years ago. So here we are in the modern warming period with a little ice age. 1300 to 1850. It was very cold. The alpine glaciers were all growing again and whatnot around the world. Then we had the medieval warm period, where grapes were grown in northern England, vineyards. And we haven't reached the temperatures yet of the medieval warm period. 2,000 years ago was the Roman warm period, much warmer than today. And then 3,500 years ago, the Minoan warm period, again, much warmer than today. Civilization flourished in all these warm periods, and things get difficult in these cold periods. Okay, so we'll take a closer look at the last 1,000 years. So the last 1,000 years looks like this. Okay, so here we are in the medieval warm period, coming out of the warm period into what's known as the little ice age, and we reached this Maunder minimum about year 1600. So that was the depths of the ice age, or the last little so-called little ice age down here. And since that time, we've been on a warming trend for 425 years now. It's been gradually warming. So it's a black line, but it's not warming in a uniform manner. What's happening is everything just keeps cycling and cycling, the cycles within cycles within cycles, as we mentioned. Warming, cooling trend, warming trend, cooling trend, warming, cooling, warming, cooling, warming trend, cooling, warming, cooling, and warming. This one is interesting. In 1940 to 1975, when human carbon emissions were exploding, we were in a cooling trend. In 1975, okay, the US Army Corps of Engineers reacting to the climate alarmists came out with their plan to save the planet from the impending ice age and spread black carbon dust over the Arctic in order to melt the ice and prevent that irreversible and impending disaster. Well, so happens in 1976, we're back into a warming trend. And by the late 1970s, you had a group shouting, we're going to warming, we're going to fry and die. And you had another group shouting, we're going to freeze to death. And both groups shouting, shut the petroleum fossil fuel industry down. It's causing freezing, it's causing frying. So, and you know much of the story since then. Okay, so if you want a really detailed look, okay, this is a detailed temperature data from the ocean's surface, modern data, okay, starting about 1981, going to about 2012 in this case. The blue is ocean temperature. The red in the background is land surface temperature, global surface temperature, and the green is CO2 fluctuations. This is done on a 12-month running basis, so on kind of an annual look at it. In all cases, okay, the temperature in the ocean and the surface warms, CO2 falls, cools, CO2 drops off. Warms, CO2 follows. These are minor perturbations. Okay, these are not major. These are minor. These are the little perturbations within the bigger cycles, and so on. So it shows up, I think, fairly clearly on this particular slide. This is from a group of Norwegian scientists who gathered, got a hold of all the data, plotted it out this way. Okay, so what is causing all these climate variations throughout Earth history? Well, the physicists and astronomers have known about the Milankovitch cycles for at least the last 100 years, where we have an eccentricity to the Earth's orbit, which brings the Earth closer and further away from the sun on a 100,000-year cycle. So there's a major glacial cycle in those glacial warm periods, and also 413,000-year cycle in there, 20,000-year cycle related to the precession of the Earth, it wobbles like a top, and the 40,000-year cycle related to the tilt of the Earth, which is the tilt change of solar, which impacts the way in which solar radiation impacts the Earth. So changing both intensity and the manner in which it impacts the Earth. In addition to that, okay, solar intensity, magnetic fields there on the sun are varying on 11, 22, and longer year cycles. Okay, there's a whole bunch of things that are going on related to the sun and the planets. Okay, but the oceans they're the major absorbers, retainers, and distributors of solar energy. And those ocean currents, okay, we've all been told this and know this, it controls annual, decadal, and longer climate variations. And I just a little reminder here that water, right? Water on a per volume basis has, well, it's 2,892 times the heat capacity of CO2 gas, or 3,200 times the heat capacity of the Earth's atmosphere, which, and it's also 5 times the heat capacity of rock. Okay, so water is the great absorber of heat. What basically that means is that if the atmospheric temperature warmed by 1 degree, it would take centuries, if not a millennium, for that atmosphere at a sustained higher temperature of 1 degree to warm the ocean by 1 degree. Whereas temperature effects from ocean current changes like El Nino, okay, affect us thousands of kilometers away immediately and sometimes quite significantly and dramatically. All right, so just summarize the controls. We're getting near the end here. Controls on Earth temperature and climate. So solar irradiance variations and magnetic field variations. So we haven't talked about how that affects things, but it can affect cloud cover. Earth orbital changes, the eccentricity, precision, tilt. Okay, water is vapor, liquid, ice, clouds, ocean absorption, storage, okay, and redistribution of heat, the magmatic and the volcanic activity, the geotectonic cycle, cosmic and solar particle radiation variations, which we haven't talked about, but that affects cloud cover and all other things, and then the biosphere, which is significant. Okay? So it's all affecting the climate over time. There's cycles within cycles within cycles within cycles, and we can go all the way down for these, the short scale annual cycles. So, catastrophe, okay, climate predictions. What are they based on? Computer models. Okay, this is a graph that shows 102 computer model runs in 32 groupings, and then the red line is the average of all these computer runs, showing a dramatic increase in temperature. And the scale here is 1977 up until 2023. Okay, so there's the computer models. Down here in blue squares, we have pre-satellite data sets, actual measurements, okay, in blue and green. That's the average of 4 balloon data sets. Okay, 30 million balloon temperature measurements all through the atmosphere since 1950. Okay, and they show quite a different story. It's warming, but at a much lesser, slower degree. And in the last couple of decades, things have really kind of slowed down in terms of warmth. So all these disastrous predictions you've heard about, I'm only putting one here, and you've all heard of dozens and dozens. They've come and gone. Is it, and this is from a University of California physicist, John Holder, 1986. It is possible that carbon dioxide climate-induced famines could kill as many as 1 billion people before the year 2020. Okay, well, what actually happened is carbon dioxide has fertilized the planet and resulted in enormous crop increases in production. Right? And I've talked to local farmers, have told me some amazing stories about what they've seen over the last, several decades. It's phenomenal, to say the least. Okay, so I think this is maybe the last thing before we summarize. What's the deal? Deaths from all climate disasters dropped by 95% over the past 100 years. This comes from the International Disaster Database, published in the Wall Street Journal. So it's not, you can look this up and you can find all this information yourself. We're not gonna fry and die, okay? And we're not gonna get blown away by a hurricane or whatever. In fact, we've become very good at mitigating the disasters and predicting them and taking the necessary precautions. So we're doing just fine as a human species. All right, now summarize and then done. Okay, quickly. Climate. It's always varied in cycles within cycles within cycles within cycles. There's no evidence in the geological past that CO2 drives temperature, and the greenhouse effect is in fact overwhelmed by water. I'm not saying there's no CO2 effect, but it is overwhelmed by water. Climate variations are driven by changes in solar irradiance, and that solar energy is stored and redistributed by water, oceans, atmosphere, and ice, which then affects climate variability. Other climate and atmospheric impacts have come from volcanic and geotectonic activity and the Earth's marine and terrestrial biosphere. So increasing CO2 and warming have always been good for life. Cooling and low CO2 has resulted in this severe stressing of life. Okay. These climate models, as far as I can see, they appear to ignore key geoscientific data conveniently. And I will say with emphasis, finally, that is inappropriate to conclude that there is a warming crisis caused by human CO2, when in fact the temperature trends fall within natural Earth cycles. So if you want to talk about a crisis, you've got to show that there's something happening which is beyond normal Earth natural cycles. I'm not saying there isn't, but I haven't seen it. And I'll conclude with that. I hope this is a happy talk and a good news talk. Okay, I'm sorry I cannot bring you another disaster talk of gloom and doom. I can promise you that you're all going to go to bed tonight. You're going to wake up tomorrow and the Earth is going to be just as happy and comfortable as ever was, doing exactly what it should be doing, in spite of the massive pressure otherwise. Okay, so thank you for that.
Floor is now open for any questions. I'm sure we have some questions for him.
Thank you. What, I silenced the crowd?
Why did you use the word evolution in your title? I don't see any evolution.
Well, there's actually a lot of evolution going on. The planet itself is constantly evolving. It's nonstop evolving. Life of course, is evolving along with it. So it's the changes in the, the earth that we're referring to.
I see that CO2 temperature graph again. I noticed something.
Okay,
This isn't being like,
be nice.
you guys. Past it,
Past it?
yeah.
Which one are you?
It's the one with the green, the,
Okay, that one? Yeah,
so the blue is the water temperature, right?
surface ocean water temperature.
So there, the peaks of the temperature are, there's like a 2-year delay with the peaks in this carbon dioxide, yeah.
Actually, these guys have done the work, okay? And they say that it's a 9 to 11.5 month lag.
Okay, I didn't see
Yeah.
that.
Sorry.
So anyway, what I was gonna suggest is that, could that be like the ocean acidifying and deacidifying?
I don't, no, the ocean doesn't change its acidity that rapidly. There's, like the estimates that I've seen on ocean acidification is that it's changed by from, 8.2 to 8.1 over 170 years. So that's the kind of the scale at which that takes place or may take place, and that's probably only in the very surface waters that's happened.
Well, even the concentrations you showed in the beginning, I was thinking about the ocean acidification. I'm just like, if that's how much it's gone up. The CO2 emissions have gone up. I don't see how, like, the ocean acidification would be a problem at that point. You're in such small concentrations.
Well, it would have to be a very, very, very long-term effect. And the thing is, there's buffers too. There's things that will counteract the acidification. So it's not a one-way kind of a reaction that's going on. Thank you for that. Any more questions? No.
I was curious about those black smokers and the white smokers there.
Yes.
How many get discovered, say in 10 years or 5 years or whatever number you want to pick, like, and how many people are actively looking for that sort of thing? Or are they just discovered as a result of looking for something else?
Yeah, it was
the story that.
Yeah, the first discovery of black smoker is like about 1980 or something like that. Don't quote me, I don't know the exact. But since then, there's something like 415 black smoker fields. Okay, well, there are fields of
There's
this
the
thing
field.
that they know of. They don't come
Yeah,
one off,
yeah.
So, but you're absolutely right. It's extremely costly to go on one of these adventures looking for black smokers. So, there may be, I don't know, there may be hundreds of thousands, maybe a million of them out there. We don't
We
know.
might know about 0.01% of them, or
Yeah, yeah.
we have no idea.
Yeah, we have no idea. I mean, there are parts of the world that are much, are hardly explored. We don't know much about, never mind the bottom of the ocean.
Yeah.
Yeah, but they're there.
So why is this not more widely known and talked about? If there's enough data that supports it? And why are we continuing to enforce so many regulations and restrictions on CO2 emissions? If there's so much evidence that it actually causes.
Yeah, well, that is the question. Very good. Everybody hear that? If this is the case, how come this isn't widely known and why are they still trying to force all these regulations on us and so on and so forth? Well, according to the IPCC and the Governmental Panel on Climate Change, the science is settled. Okay. And dissenters need not say anything, basically shut up. So among other things, that this climate business has become not a multi-billion, but it's become $1 trillion industry. So there's a lot of pressure to perpetuate it, I would say. They, when IPCC is looking at this, their 2,500 reports, okay, and they have consensus that, we've got a climate problem. If you look closely, what is the consensus? First of all, consensus is not a scientific term, okay? There may be one person in, 8 billion who has the right idea, okay? So truth is not dependent on, putting up your hand and consensus. But when you look at what is the consensus is that everybody agrees climate's changing. 100%. Okay, everybody agrees it's getting a little bit warmer. 100%. Everybody agrees CO2 is increasing. 100%. Consensus. It's not even 100% consensus on those things. But when it comes down to statements like there is a definitive statement that there is a human CO2 caused climate crisis. Okay, the number of these papers and scientists that actually say something like that is about 0.5%. So as young people, you're asking the right question. What's going on? Red flags, okay? I mean, when I was president of Geoscientists Canada, it's all about the integrity of the profession. That's all we dealt with, okay? Red flags, when people tell you you're not allowed to have an opposing opinion, okay? Something's wrong. Or when the science is settled, there is no other opinion that's allowed, something is seriously wrong. Okay, the red flags go up immediately. Okay, it wouldn't matter if I was the only person on planet Earth who took this contrary position. I have the right to say it, and I have the right to discuss it and to debate it. Okay, and you have the right to say whatever it is you want to say and debate it openly, but they won't do that. They simply will not.
Yeah,
I've also when you look at a lot of presentations, they'll be looking at data from the last ice age onward rather than going back further. And that's easy to determine if it's okay, global sea levels have risen since then. But how have global sea levels been over time? They're following, they're just staying things. Trends that are seen there, carbon dioxide parts per million over time. Yeah, been higher, but if you look at this since the last ice age, and it looks like it's rising.
Yes,
We've been around longer.
since you mentioned global sea level, I'll make one comment. Since the last ice age, sea level has risen. I think Simon, you might know this better than me, 130 meters or something.
Yeah.
About 130 meters. But one of these climate disaster predictions has been that the South Pacific Islands are going to disappear underwater by 1990, by the year 2000. Oops, sorry, we meant 2010, and the coastal cities are going to flood. Well, guess what? The most recent study that I read on these 700 of the Pacific Islands, they've actually grown in size. The majority of them have grown. Some have shrunk. The majority of them have gotten bigger. Why? They're coral, many of them are coral atolls. Okay? Coral is constantly growing. If the sea level rises by a millimeter or two, the coral, it just grows equally fast, and they build up. And the other thing is they're all sitting on volcanoes. What do volcanoes do? They swell, they shrink, they swell, they collapse, and the coral keeps up with it. So there's a lot of things that you have to look at. Yes, go ahead.
I did have one question. It's been a while since I've dug into this, but I've heard that based on things like the molecular cycles, we should be in a slightly cooling period. So if that is the case, which like I said, I don't know if it is, you could confirm or deny it. But if we are supposed to be in a cooling phase, is the rise in temperature at least consistent with the kind of temperature fluctuations we see in those cooling periods?
Well, first of all, I don't know the answer to the question. I don't know if Austin, our local astronomer, knows where we are in the cycle. The thing is, there's so many cycles within cycles, so many things affecting those cycles. So sometimes you may be in a greater cooling trend and then you're getting a sub-warming trend within that. And it's happening all the time. So I don't know the answer to your question. I've heard a number of things said that we're in a cooling for this reason or that reason. The one thing I would say is that, you know, following the current warming trend is gonna be another cooling trend. That is coming, if we're not already heading in that direction. You know, I certainly don't expect to see the warming go on forever. It's just not gonna happen. It's never happened. CO2, you notice that when the CO2 levels were at 4,500 ppm, Earth went into an ice age, like one of these great 15 to 20 million year long ice house periods. They got absolutely nothing to do with the CO2. They're completely decoupled. So.
Thank you.
I am sure I didn't answer, I know I didn't answer your question where you.
But yeah, no, that's fine.
Any more questions?
You know, like getting on to cooling, one bizarre thing. The upper atmosphere in the last 10 years has cooled by 3 to 4 degrees. That's satellite measurements. And if you go to NASA site and other websites and you look up what's going on, it will say that its upper atmosphere is cooled 3 to 4 degrees, and it's caused by a phenomena known as greenhouse cooling, where CO2 is such an efficient emitter of radiation that it's cooling the upper atmosphere as the CO2 content rises slowly in the upper atmosphere. And I ask you to think carefully about that one. If that makes any sense at all, please send me an email and explain it to me, because I can't make any sense of that. So is that an indication that we are gonna, you know, drop back into another cooling trend for one reason or another? I don't know. I don't know the answer. I actually have. Let's see if I have that slide by any chance. Oh yeah, there we are. Okay, cool. This is a quote from NASA. This phenomenon is known as greenhouse cooling due to CO2 efficiently radiating heat into space. You know, your job as the next generation, okay, is to, you know, think hard and long and question everything. You know, maybe I'm totally wrong. You know, bring a fact, bring the facts. I will change my tune and my story in a heartbeat, because I can't stand being wrong with stuff. It's embarrassing.
Any more questions? Okay. I think that's it. All right, so let me take this opportunity to remind you of next week's presentation with Dr. Pamela Rutherford, using iNaturalist to document species adventures in Southwest US. All right. Thank you again, Dr. Mumin. I